Objectives of today's lecture will enable you to understand some important terms which are used in organic chemistry, radical substitution reactions. We are going to discuss about oxidation and reduction of organic compounds and the nomenclature of alkenes. Before starting chemical reaction, these are some important concepts and terms that you have already studied. Let us recall all of them. What are ions? A charged species that is formed from a neutral atom through the loss or gain of electrons. For example, sodium ion, chloride ion, oxide and magnesium ions. There are two types of ions, cation which is formed by the loss of electron and anions which are formed from the gain of electrons. You're also familiar with the term radical. It is an atom that has an unpaired electron and has no charge. It is electrically neutral species, contains odd number of electrons. For example, chlorine radical and bromine radical. Students, you know that mechanism of a chemical reaction are the sequence of steps through which the reactants are converted into products. We use curly arrows to describe the mechanism of a chemical reaction, so it is very important to know what these curly arrows mean. For example, this curly arrow shows the movement of a pair of electrons from tail towards the head. Means this arrow is going to show that a pair of electrons is going to move from this position to this position. Means from one molecule to another molecule. Similarly, this curly arrow, which is having a half head, it is called a half arrow, shows the movement of a single electron, not a pair of electrons. Students, during a chemical reaction, some old bonds are broken down and new bonds are formed. So let us see what is the meaning of cleavage of a bond. A bond, when it is broken down, follows two types of cleavage or breakage. First one is the homolytic cleavage. Homo means same. It means that equal distribution of electronic density or a pair of electron. Electronic density means the bond containing two electrons. For example, look at the cleavage of methane, in which I am going to show the breakage of this CH bond. As you can see that this is a half arrow. This bond represents two electrons. When this bond is going to broken down, each electron will be taken up by the individual pairs. One electron will go towards hydrogen and the other electron will go towards the methyl group. As you already know that half-headed arrow means the transfer of a single electron. One electron is going to move towards hydrogen, other towards the methyl. And this cleavage will result in the formation of radicals, which is a methyl radical and a hydrogen radical. So homolytic cleavage always results in the formation of radicals. The second type of cleavage is heterolytic cleavage, in which unequal distribution of electronic density is going to take place. For example, look at methane. This CH bond is going to be broken down in such a way that this pair of electron is going to be taken up by this CH3 group, depriving the hydrogen from its own electron. As you can see, I have placed a complete headed arrow showing that a pair of electron is going to be transferred from tail towards the head. Such type of cleavage always results in the formation of ions, a cation and an anion. This negative charge is showing that the complete pair of electron is taken up by CH3 group and the hydrogen is deprived of the electrons. Another frequently used term in organic chemistry is a nucleophile. Now let us see what is a nucleophile. Nucleophile is an electron-rich species. It has ability to donate a pair of electron, for example chloride ion and oxide ion. As nucleophile is rich in electron density, therefore it can donate it to any electron deficient species. For example, you can see this methyl anion. The opposite of nucleophile is an electrophile. Electrophile is a electron deficient species. It has ability to accept a pair of electron because it is electron deficient. So it can accept a pair of electron from the nucleophile. Let us take an example and apply all the concepts that we have learned so far. Take an example of bromination of methane, which is showing the movement of electron pairs. As you can see, the bromide ion having a negative charge will act as a nucleophile. This complete headed arrow is showing the transfer of a pair of electron. Negative charge means pair of electron. It will be transferred towards carbon having a positive charge, which is acting as an electrophile. So the transfer of electron will result in the formation of bond between carbon and bromine. Let us look at the same example, but these are the Lewis structures. You can see that this bromide ion is having a negative charge over here, means a pair of electron, which will be transferred to the carbon, which is having 2 electrons less. Its octet is not complete. 2, 4 and 6 electrons. So this bromine atom over here carrying a negative charge can donate or share it with this carbon atom to complete its octet. In this way, a bond will be formed between carbon and bromine. So this complete headed arrow is showing you the transfer of a pair of electron from the nucleophile towards an electrophile. Now let us take an example to show the movement of a single electron through a half-headed arrow. The example is the formation of hydrochloric acid, which is going to show the movement of a single electron through a half arrow. As you can see, I have taken a hydrogen radical, a chlorine molecule. The bond between chlorine molecule is going to break down in a homolytic fashion. 2 chlorine radicals are going to generate as a result of cleavage of this bond. And a bond is going to form between this chlorine atom and this hydrogen radical over here. This electron and the radical of this chlorine is going to join together to make a bond between hydrogen and chlorine. This half arrow is showing the movement of a single electron. Now let us look at the Lewis structures. This is a hydrogen having a single electron. This is a pair of electron showing the bond between these 2 chlorine atoms. Now you will see that one of the electron is going to move over here, generating a chlorine radical, which is going to make a bond with this hydrogen radical. Whereas this X representing the electron is going to transfer from this bond towards this chlorine atom, generating another chlorine radical. In this way, a bond is going to form between H and Cl, generating another chlorine radical. So these half arrows are representing the movement of a single electron. Now students, let us study the radical substitution reaction, which is also called free radical mechanism. They are also called photochemical reactions because they take place in the presence of sunlight. 3 steps are involved in radical substitution reaction, which are initiation, second step is propagation, and the third step is termination. You can look in your textbook. This is the radical substitution reactions which are given, but over here I am going to explain each and every step in detail. The first step of radical substitution reaction is initiation. Let us see how it takes place. It takes place in the presence of heat or UV light, ultraviolet light, which cause the weak halogen bonds to undergo a homolytic cleavage and generate bromine radicals and start the chain process. Look at this chemical reaction. You can see there is a bond between these 2 bromine atoms which are going to be broken down in the presence of heat or sunlight in a homolytic manner and generate 2 bromine radicals. As you know that radicals are chemically active species, so they are going to start the chain process. The second step after initiation is propagation, in which the bromine radical which was formed in the initiation step abstracts a hydrogen from methane to form HBr and a methyl radical. This methyl radical that is formed, it is going to abstract a bromine atom from a bromine molecule. Let us look at the chemical reaction. So this is the bromine radical which was generated in the initiation step. It is going to make a bond with this hydrogen atom after the homolytic cleavage of this CH bond, generating a methyl radical and making a HBr neutral molecule. In the second step, this methyl radical is going to abstract a bromine atom from a bromine molecule. The bond between these two bromine atoms is going to broken down homolytically. A bond is going to form between bromine and this methyl radical, making methyl bromide and a bromine radical. This process is called propagation, in which a neutral species is formed, but along with a radical. So the reaction do not stop here. It is going to proceed further. That is why it is called propagation. The third step of radical substitution reaction is termination. As you already know that the word termination means to put an end. So it is the last step. It is going to terminate this chemical reaction, in which various reactions between the possible pairs of radicals forms ethane, bromine molecule and methyl bromide. These reactions remove all the radicals so that the cycle do not continue any further. Let us look at the chemical reaction. All the methyl radicals that are formed are going to make a bond and convert into ethane. Similarly, all the bromine radicals that are formed can make Br2, or the cross reaction can also occur between methyl radical and bromine radical to make methyl bromide. Now you can see that all the reactions are producing neutral species. So all the radicals that have been generated are consumed. There are no further radicals and it is going to stop the chemical reaction, means it is going to terminate the chemical reaction. Students, here are some important notes with reference to the radical substitution reactions. Substitution of RH means alkane, by X means this H hydrogen atom will be substituted by X stands for halogen, provides an alkyl halide. R and X is going to make an alkyl halide, and HX, this H is going to make a bond with another X atom. Alkane RH relative reactivity order is that tertiary is having greater reactivity as compared to secondary. Secondary is greater than primary. Primary is greater than methyl. Halogen reactivity order is that fluorine is having greater reactivity than chlorine, which in turn have greater reactivity than bromine and then iodine. Only chlorination and bromination are useful in laboratory and reaction proceeds via radical mechanism. Let us look into the detail of each and every point over here. The first point describes the reactivity order. Now first of all, let us see what is the meaning of tertiary, secondary and primary. Tertiary carbon atom is represented by 3 degree. It is a carbon atom attached to 3 other carbon atoms, whereas secondary carbon is a carbon atom attached to 2 carbon atoms and primary carbon is a carbon attached with 1 carbon atom. This is an example of a tertiary alkane in which you can see that this carbon atom is directly attached with 3 carbon atoms. So this carbon will be called as tertiary carbon. Tertiary carbon atom over here is directly attached to 1 hydrogen atom. Because of the bulkiness of these 3 alkyl groups, you can see that reactivity of tertiary group is the greatest among the 3. Why? because this hydrogen can easily be substituted. The reaction is going to be fast. Secondary carbon atoms show reactivity less as compared to tertiary. Secondary carbon atom is a carbon that is attached directly to two carbon atoms. For example, you can see that in this structure, the central carbon is directly attached to two carbon atoms, making these hydrogen atoms a little less reactive as compared to tertiary, because over here the strain or the crowding is a little less as compared to that of tertiary carbon. The reactivity of primary carbon atom or primary alkane is less than that of secondary. A primary carbon atom is that carbon which is directly attached to one carbon atom or none, as you can see in the example of methane. Now over here, the bulkiness or the crowding is further reduced in comparison to secondary and tertiary, making these hydrogen atoms more unreactive and more stable. In methyl, you can see that there are no alkyl groups attached, making these hydrogen bonds more stable and less reactive. Now let us see how the crowding around the central carbon affect the reactivity of tertiary, secondary and primary alkanes. In the first example, this is tertiary. You can see that this hydrogen atom is going to feel quite a lot of strain due to the crowding around it. As you know that methyl groups are going to have a tetrahedral geometry. So there is a lot of strain on this carbon atom. In order to remove the strain, it is going to break this CH bond very readily. In comparison to tertiary, the strain due to the presence of alkyl groups is a little less as compared to tertiary, because over here we are having only two methyl groups. It is less crowded. So these two hydrogen atoms are a little stable as compared to tertiary. It is not going to feel as much strain as the tertiary hydrogen. Similarly, in the primary structure, over here you can see the strain is further reduced due to the presence of only one methyl group. So these hydrogen bonds and this carbon is more stable and less reactive. The second point was about the reactivity of halogens. The order of reactivity is fluorine is greater than chlorine, which is greater than bromine, which is greater than iodine. Fluorine is very reactive molecule. Its reactivity is very high. All the chemical reactions are violent. Whereas iodide ion, it gives very slow reactions. Chlorine and bromine are moderate. Therefore, chlorination and bromination are useful in laboratory. The reactions all proceed by a radical mechanism. Students, it's time for you to recall your previous knowledge. What do you understand by oxidation reduction reactions? Think over it. Oxidation can be addition of more CO bonds, less CH bonds, loss of electrons, or increase in the oxidation state. For example, from +1 to +3. All are the examples of oxidation reactions. Reduction involves the addition of CH bonds or less CO bonds, gain of electrons, or decrease in the oxidation state. For example, from +1 to -1, this is a decrease in oxidation state. Now students, let us start alkenes. Acyclic unsaturated hydrocarbons containing double bonds are called alkenes. Each carbon atom of alkene which is making a double bond is sp2 hybridized, having a triangular planar geometry. So this carbon atom over here is sp2 hybridized, making a triangular planar geometry. Now let us study the IUPAC rules for naming alkenes. You have to select the longest continuous chain containing the double bond, which will be the parent chain. The ending name "ane" of the alkane is replaced by ene, E-N-E. The chain is numbered in such a manner as to give minimum number to the double bonded carbon atom. Look at these examples. In the structure you can see that I have a long chain containing 5 carbon atoms. 1, 2, 3, 4 and 5. But this chain is not including my complete double bond. So I am not going to select this as my parent chain. Instead, I am going to start numbering from here including the double bond 1, 2, 3, 4. Although it is not the longest chain, but it contains my double bond. Secondly, I am going to number it in such a way to give minimum number to the double bond. That is why we have to start numbering from this carbon atom, because it is giving minimum number to the double bond. If I start numbering from here, carbon number 1, 2, 3 and 4. But if I started from numbering here, 1, 2, 3. 3 is the number which we will give to this alkene, which is going to be wrong. The next rule is that the position of double bond is indicated by the lower number of the carbon atom. For example, as you can see in this structure, the double bond is present between carbon number 1 and carbon number 2. If I am going to name it 2-ene, it is going to be incorrect because I have to mention the lower number. So instead of 2-ene, it should be 1-ene. The next rule says the lower number of carbon is placed before the name of the parent alkane, and if alkyl substituents are present, their names are added by the rules that we have already studied in alkanes. Look at this example. A methyl group is present on carbon number 3 and ethyl is present on carbon number 2. So these are the two substituents which we are going to name according to the rules of alkanes. But the position of this double bond is going to be represented by the lower number, which is going to be placed before the parent chain. So the name of this compound is 2-ethyl because carbon number 2 contains ethyl substituents. 3-methyl, we have a methyl group on carbon number 3. Since the double bond is present between carbon number 1 and carbon number 2 and we have to mention the lower number. So it is 1-butene because the longest chain contains 4 carbon atoms. Instead of butane, we have written butene, E-N-E. Next rule says that the presence of more than one double bond, you can have a chain containing more than one double bonds, then you have to indicate it by suffix diene or triene for 3 double bonds and so on. For example, we are having 2 double bonds in this pentane chain, one between carbon number 1 and 2 and the other between carbon number 3 and carbon number 4. The name of this alkene is going to be 1,3-pentadie. Di is the suffix that we are going to add and ene for alkene. Why we have added 1,3 over here? Carbon number 1 and carbon number 2 is having a double bond, but we have to mention the lower number. Similarly, the other double bond is present between carbon number 3 and carbon number 4, but again we have to mention the lower number. So the name is 1,3-pentadiene.